Good afternoon, and good afternoon to all of you who are online as well. Welcome to the Don P. Giddens Inaugural Professorial Lecture. It is truly, I've said this every time, and I will say it again, this is one of my most favorite events to take part in, and it's a pleasure to be here to join you in honoring Professor Mounya Elhilali. Mounya is the Charles Wren Faculty Scholar in Electrical and Computer Engineering and the founder of the Department of Electrical and Computer Engineering's Laboratory for Computational Audio Perception. She's also a member of the Center for Language and Speech Processing. And since she joined Johns Hopkins as an assistant professor, she has built an impressive research record, developed productive interdisciplinary partnerships, and has been an exemplary mentor to her graduate students. Her research focuses on the computational and neural basis of sound and speech perception and behavior, bridges the fields of neuroscience and audio technologies. And through her work, she's provided new insights into brain science. Her research has included the development of new audio technologies that have applications in a broad range of health-related fields, which I'm sure she will tell you all about, and so I won't go through the list, but really the work that Mounya has done has been both impressive for its technical depth and impressive for the practical real-world impact it has had. And so she's received broad recognition for her work from numerous professional societies. She's the recipient of both the Office of Naval Research Young Investigator Award and the NSF Career Award, as well as a Johns Hopkins University Catalyst Award, which recognizes outstanding creative and collaborative research. Mounya's talk today is on the science and engineering of listening. I emphasize, listening. Just saying that to the audience. But before we hand the floor over to Mounya, I'd like to take a moment to recognize one of my predecessors, Don Giddens, for whom this inaugural professorial lecture series is named. Don Giddens was the 5th Dean of Engineering at Johns Hopkins and a professor of mechanical engineering. And like Mounya, his career has been defined by commitment to both research, education, and mentorship. And now, with that, it is my pleasure to introduce Pedro Irathaqui. Sorry, Pedro. Irathaqui. Professor and head of the Department of Electrical and Computer Engineering. Pedro. And I will say one thing, that anyone with the last name Schlesinger shouldn't have trouble with other names.
It's a doozy of a name, so I completely understand. Oh yeah, so the mask facial recognition thing doesn't work, and I'm gonna need this in a minute. So thank you very much. So I first got into neural engineering in my field because I was born with a congenital hearing defect, and I was very interested in how hearing and hearing processing worked. When I found out about your research, Mounya, I was thrilled, and I'm really excited about hearing about it today and hearing it from you. I am so excited and so honored to be amongst your colleagues now that I'm here at Hopkins. But today it's my honor not to present you, but rather to present your mentor, Dr. Sharma, who received his, hence the iPhone, who received his BS degree in 1976 from Imperial College in London, his master's and PhD degrees in electrical engineering from Stanford, and this is really cool, his Master of Arts in Slavic Languages and Literature from Stanford at the same time as his PhD. Dr. Sharma has been a member of the University of Maryland faculty since 1984. He has been associated with the Institute for Systems Research and received a joint appointment there in 1990. He's a fellow of the Acoustical Society of America and a fellow of the Institute of Electrical and Electronic Engineers. So with that.
You mind if I take this? Uh-oh, 6 feet.
You're a visitor, you're allowed.
Yeah, so I'm just going to give a few brief remarks, and brief they will be because I've been instructed that 5 minutes is my limit. And during that time, I'll tell you about my acquaintance with Mounya and the decades of research we did together, and after her graduate work, and also her achievements and all that. That's all in the instructions in the 5 minutes. So, which is just as well that I should stop, because as you all know, when you let an advisor or a parent talk about their offspring, you'll never hear the end of it. And so I will limit myself to 3 anecdotes of a time when, before most of you knew about Mounya. And one of them is about this time of year, many years ago, 20 some years ago, when we have applicants, I had these 3 sacred rules that I always follow. The first is just not to read any letters at the time or emails, because I let the committee of the department take all these applicants and all that stuff. I don't know why, but I read one letter or email from Mounya. And normally I would just sort of turn my gaze and continue working. But that time I was so impressed with the Mounya's letter and email that I actually went out of my way, arranged for a phone call to call her in Morocco. At the time, that was not a trivial task. And then, so that rule went by the wayside. And the second rule was never to offer a GRA sight unseen. And I would like to have the student work for a few months, and then they can be sure that they like what they see and so on. Well, after talking to Mounya about 5-10 minutes, I already had made up my mind and made the offer. So that's rule 2 that was, she managed to shatter. And the third rule was really important to me at the time, was that, you know, our EE students are really smart, and it's easy for them to want to basically do algorithms and computational models and data analyses and all of that. They just didn't want to train animals and do recordings with these animals day and night and do surgeries and all that. But I insisted that every student had to do this as part of their education so that they know what biology looks like. Well, Mounya also convinced me with her exquisite sensitivity to what biological data are like. Her Midas touch, every time she looked into any piece of data, it had some gold to produce. And so that rule also went by the wayside. And so thanks to Mounya, I'm a lot better and more kinder advisor than I at the time that I was. And so I just want to thank you really, really for the luck that I had to cross paths with you, and the joy that I've had over the years working and thinking and arguing. That was just so wonderful to be able to do that. And finally, for inviting me to do this now, because the kind of feeling I have is really the kind of feeling that, as I said, as an advisor or a parent has about seeing their offspring achieve such beautiful achievements and be happy. And Mounya was one of those people who made everybody around her happy, no matter where she was. So thank you very much, Mounya.
Thank you. All right, well, thank you everybody for this really lovely introduction. I'm truly honored and really touched by all these kind words. So as I guess you see in the program, the title of my talk is The Science and Engineering of Listening. And I wanted through the talk to touch upon different areas of work that we've been doing, exploring this concept of listening, basically. And so I'll start with a sort of a pretty trivial observation that the world around us is a pretty noisy place. So sound around us exists wherever we go, and we don't really live in soundproof rooms. You know, as you're listening to me right now, there is hissing coming around and all kinds of sounds coming from everywhere. And while we don't really think about it much when we communicate with each other, but the actual processes that go on that allow us to pick out certain sounds and ignore others are not trivial. So this is a quote that basically tries to highlight that, and it basically says that listening is not the same as hearing. It's really an active process in which our experiences, our goals, and expectations really constrain and control sort of how we listen in very complex ways. And so to translate this quote into sort of more engineering terms and to say, well, what is hard really about listening? Listening is really an underdetermined optimization problem. So if you imagine you're going about your daily life, you're in at a party, or even in these days of masking, we're still interacting with each other. And imagine you want to listen to somebody, and that's the signal X of T. What you're really hearing is not this signal. You're hearing basically a version of this signal after the sound travels and undergoes all the constraints that sound propagation imposes on it. And in addition to that, you have the sound that you're interested in, but you may also have other sources in the environment that are present that also undergo a whole bunch of transformations. And all of these things together are basically the sound that you hear. So if you think of this as an optimization problem, this is your observation, this is your known quantity, and everything else is your unknown. That's a single equation with so many unknowns and one observation. And that's basically the definition of an underdetermined optimization problem. Now, what the brain does is it has to look at this observation and try to entangle or put some constraints to allow it to map this input, this messy input, in order to be able to extract this signal that you're interested in, X of T, in order to understand it, guide behavior, learn from it, interact with the world around us. And so there's many things that we know about how the brain processes this kind of sound to map this Y of T and be able to extract this X of T from it through a number of transformations in the biological system. But at the same time, what we also know is that the brain does not really dedicate resources to processing all the information. So we know we cannot process all the sensory information at once. This is sort of an example from real life. This is an aviation accident. This is United Flight 173 that went down near Oregon. And basically what was happening is that the pilot was focusing on a landing gear malfunction that they just didn't pay attention to an alert that was alerting them to the fuel running low. So this is a simple example from real life where the information was available, but the processing resources were not dedicated to the right piece of information. So one of the goals of the research that we've been doing is trying to understand how does the brain allocate these resources in order to pay attention to certain sounds amidst other sounds that surround us. So if we look at the auditory system, if we take basically a cross-section of the auditory system, we know that when sound enter our ears, they go through a number of transformations that biology has evolved to facilitate the process of entangling these sounds that we hear in everyday life. So this is basically what is considered as a simplified diagram of the auditory system, sort of looking at different processing stages. And the only reason I'm showing you this diagram is to basically highlight that the brain is really structured along multiple layers or processing stages in a somewhat recurrent yet still hierarchical fashion. And so this is very reminiscent of the structures that we often use in artificial neural networks, where the input gets mapped onto increasingly complex latent spaces. And so the mapping from the input undergoes a number of transformations where some mapping function controls the complexity and the spaces onto which these mappings or these latent variables are represented. And so one of the, I guess, accepted hypotheses about the role of this hierarchical structure is that the auditory system, what it's doing through these transformations is it's entangling the sound stream manifolds into separable ones so that we are able to pay attention to this voice, or maybe if our phone starts ringing, we shift our attention to that sound. And so having access to these representations through these different transformations facilitates this process. So one of the key questions I wanted to focus on in today's talk is how does our attention, our ability to pay attention to one sound, how this attentional feedback modulates information processing. And this is a topic that has garnered a lot of interest in the research community, spanning both the neuroscience community and also the computational or artificial intelligence community. And in basically the most recent 5 years, there had been a lot of interest in this topic of attention. This is a paper that was published in 2017 called "Attention is All You Need." And basically, this has set the stage to a huge revolution in performance for computational models in machine computer vision, natural language processing, machine translation through the use of these transformers and perceiver systems. And the idea here is, by imposing constraints on what kind of information you want to process. You don't want to process all the information. You can selectively attend to certain pieces of information using contextual cues. The systems are able to perform better. While this view is to some extent borrows from what the biology tells us, it still remains a little bit limited and does not fully capture the complexities of how attention operates in the biological system. And this is something that we've been looking at for many years now. And the key idea of what we're learning from experimental results is that when we pay attention, our brain almost, I don't want to say rewires, but completely adapts the way it processes information to facilitate our ability to extract the information that we care about. So in a way, we can think of this as, if we think of this whole thing as a system, the whole system function actually changes due to this attentional feedback. And we've been trying to understand what are the potential benefits of having this kind of adaptation imposed in biology? And there's two key results that I would highlight. One is that attention induces these adaptive changes to the neural properties. So the individual nodes or computing units in the brain actually change their neural properties on the fly to facilitate or to enable us to pay attention to certain sounds and ignore others. And the other one is, if you look at the activity across networks of neurons, that those also change their sort of what we call temporal coherence, the way they coexist or co-activate together. And both of these kinds of changes induce really profound changes in the way the system operates. But computationally, what we were able to find in a number of recent studies is that what attention really allows the brain to do is to reduce the uncertainty. So if you imagine that we are representing sounds along these different high-dimensional manifolds, what the feedback is doing is basically tightening the radius of this manifold. There is less uncertainty about how the sound mapping actually represents. And so in one demo application that we've worked on for speech tracking, this is basically to represent this idea. If we don't use any feedback and we try to focus on representing speech versus noise, you get a pretty broad representation if you try to mimic this kind of biological systems. But if you implement this kind of feedback, you get a much tighter, less variance in the representation. And so this is sort of what I mean by reducing the mapping uncertainty. Now, one of the complexities of studying attention in the brain is that attention is not sort of one simple sort of feedback loop. Attention is controlled, so it's not really a monolithic process. So it is controlled by both what we want to pay attention to, but also what sounds around us. So if a phone were to ring off right now, we will inadvertently pay attention to it. We may not choose to want to attend to it, but it will grab our attention. So that kind of interaction between what we want to pay attention to and what the sounds around us sort of grab our attention is something that we don't really fully understand. And so in some recent studies, just to give you a flavor of the kind of experimental work, we've recorded brain activity from volunteers that were recruited into the lab, and we've asked them to basically track a melodic rhythm that was repeating. And in the background, we played a variety of soundtracks just taken off of YouTube. And we just asked them to ignore these soundtracks and just follow these rhythmic melodies that we're giving them. So I'll play you an example just briefly to give you an idea. happened? All right, any case. So the point here is what we're trying to do here is we're trying to direct the attention of these volunteers toward a particular pattern in the sound, a particular sound source, this melodic rhythm. And in the background, they're hearing all kinds of things. They may hear a symphonic recording, they may hear children playing, and they just need to ignore those. And what we note when we look at the brain activity of people doing this kind of task is when they are able to follow this rhythm, we see an increase in the representation of the rhythm in the brain. This is what we expect from the kind of attention that I've been talking about. If the system is focusing its resources on tracking this rhythm, then we expect an increase in the energy in the brain response for that rhythm. But what was interesting is when people are getting distracted occasionally about what was going on in the background, the mapping of this energy actually reduces rather than not change. So effectively, what this is showing us is that the system function really is adapting. And these are changes that we notice within tens of milliseconds. That means there's sort of this constant rewiring that's happening that both either enhance some representation that you want to pay attention to or suppress it for you to allocate resources to something else that may be trying to attract your attention. And so this kind of push-pull interaction is happening on the fly as we're listening to sound. What was also interesting from this study is that through a connectomic correlation analysis, we see that the same brain networks are involved in both controlling what we call our top-down attention and our bottom-up attentional control. And so one of the fascinating things when we try to sort of theoretically understand what it means, that the ability of the brain to really have this kind of what we call a push-pull interaction is really a huge advantage of the system. So theoretically, we can sort of think of this attentional feedback as controlling the selection of informative channels in the brain. But by having this ability to sort of perform, pay attention to something, but also be mindful of the surrounds, the system is really performing a kind of sort of autocorrection or self-supervision so that we're not completely deaf to what's going on around us, but we are able to adapt to what's happening and improve ultimately the system performance. And the fact that the same brain networks are controlling both aspects of our attentional system really allows a more efficient computational and energy load management. So we've implemented a basic system that allows this kind of push-pull interaction and compared it to some of the state-of-the-art systems, particularly focusing on speech noise cancellation. These are in extreme noise conditions. And so this basically shows you one of the results that we're able to obtain. So these three bars show the results from three state-of-the-art systems. On the y-axis here is a signal to distortion ratio. Basically, how much are we able to cancel the noise in these kinds of signals? And so higher is better. And in red is a fairly simple biomimetic system that tries to implement this idea of this kind of adaptive interaction. And we see that we're able to really improve on what the state-of-the-art with sort of fairly extensive models by really allowing this kind of adaptation that is generally lacking in most computational models. And so the key really takeaway here is that adaptive processing is really critical for intelligent processing in the brain, but it ultimately translates into some resilient audio technologies. This is, by the way, a system that is currently deployed. This system is currently deployed in a Naval Sea Systems Command Center and is used both for sensor network communication and also for personnel decision-making training. The ability to really try to understand how we interact with sound and how we're distracted by other sounds. So in the last segment of the talk, I'm just going to switch to another application of where we've been exploring this idea of listening, and that is listening in medicine. So listening in medicine is not something new. I'm particularly referring to listening to body sounds. So everybody has, recognizes or equates the stethoscope with the medical practice. And this fact of auscultation or listening to body sounds is something that has been practiced since historical records show since the ancient Egyptian civilization. And then around the Industrial Revolution, there's been some early models of the stethoscope that have been evolving. And ultimately, what these different tools are trying to do is they're trying to solve a similar problem like I described. You're trying to record the sound of a particular body organ, a lung, a heart. You may be at the same time surrounded by other noise in that environment, or maybe the sensor, the device you're using may introduce some noise. And so combined together, this is what you as the physician would hear from the stethoscope. You hear some sound, YFT, that's what you observe. And that is a function of some signal, some sound from one of the body organs that you're interested in and some noise. But what adds the complexity in the domain of applying this in medicine is that you're trying to diagnose some unknown pathology. And so this problem gets further exacerbated if you're trying to do this under non-ideal clinical conditions. So this is an example. So where basically your ability to pick out the lung sound or the heart sound is much more faint because you're surrounded by so much noise. So this is a recording that was obtained from a mobile clinic in Zambia. And this is basically what the physician would hear. So I assume everybody was able to hear. This is a very noisy clinic. You hear maybe a motorcycle driving by. The physician is supposed to be hearing the lung. They can't hear anything because the environment is non-ideal. They are probably in an open space. They're not in a nice, doctor's office, quiet. They're able to focus on the lung. That's what they basically hear. And so this problem where basically the sound you're interested in is overwhelmed or swamped by the noise of the environment. And so listening is really a challenging task, even to the most highly trained ears. These are sounds that were sent over here to the School of Medicine for these physicians to listen to. They can't hear anything. It's just, you just hear people talking, children crying, you can't hear the lungs. And so the other challenge with trying to apply this problem of listening is that noise can often masquerade as an abnormality. You hear patterns and you can't tell, is there something wrong with the body organ that you're interested in, or is it just noise in the environment? So we've been interested in this topic because, and particularly applied to lung infections, because acute lower respiratory infections, particularly pneumonia, is the main cause of death in children under 5 years of age. There's about 1 million children that die every year of pneumonia. This is more deaths than HIV, malaria, tuberculosis combined. And unfortunately, 99% of these deaths are in lower and middle income countries. And importantly, these are really preventable and treatable with adequate tools. So these are not deaths that cannot be, prevented. And so what our main interest from this idea of listening is that sound prevents a great deal of advantages. So unlike other tools that may require either extra costs or extra medical expertise or extra time, sound is really fast. It's practically instantaneous. It is non-invasive. You're just listening to the breathing pattern. It is readily available. You don't need to engage or to draw a blood sample or anything like that. And it is extremely cheap. You don't require any fancy technology for it. The challenge is that sensing sound is very hard, especially in those environments. It can be masked, again, depending on what the surrounds are. And interpreting it is also hard. That's why you need highly trained physicians to listen and tell you whether there is something wrong with the lung. But luckily, those three obstacles are things we know a thing or two about how to handle. How can we make access to these sounds better? So over the past about 7 to 8 years, we've been partnering with colleagues at the School of Medicine and the School of Public Health through some NIH and Gates Foundation supported studies where we've been collecting lung sounds from pneumonia cases and also control cases in children under 5 years of age in a number of busy and outpatient clinics around different countries around the world. And we've been trying to rethink how can we enable access to high quality lung sounds, but also enable the possibility of automatically processing and diagnosing on the spot. And so with collaboration with these colleagues, but also some very smart students here at the School of Engineering, we've been able to basically re-engineer listening to these body sounds. So we've been able to develop this basically Hopkins device that boasts a lot of functionality. The most important of them are, it is very low cost, very few dollars of electronics. The sensor that enables the pickup of the sound has been redesigned to enable some more robust transduction. So one of the challenges with using stethoscope is it's like a tennis racket. You need to have the right positioning to get the sweet spot. And that's something we can address by redesigning the sensor so anybody can use it. You don't need somebody who's a high expert to be able to position it. Anybody should be able to use it. And one of the important pieces in this technology is that it has an integrated microprocessor. That means with the right tools, we can enable a lot of processing on the spot to make this a point of care device, something that you can use on the spot to be able to diagnose a disease and then treat the or sort of indicate possible treatment for the patient. So this is, by the way, a device that is now commercialized, has received FDA approval, and has been, I guess, enjoying a lot of success. And so the two key things that we were able to implement on this microprocessor is the ability to improve the sound signal. So by imposing some constraints that balance basically what we know about where the lung sounds should be, we're able to implement this sort of adaptive noise cancellation of ambient noise. And ultimately what we're hoping to do is we take the sound that is picked up by this device and try to process it to extract as clean a signal as possible. We've been able to validate this kind of algorithms. This was done. Basically, we presented these sounds that have been processed through this technology to a panel of experts, and 95% of them have thought that this was a far better lung sound than they would get with a commercial device. So to give you an idea of how this compares, so this is a video that was taken in the lab. So this is a state-of-the-art, basically top-of-the-line stethoscope. This is a ThinkLabs 1. This costs about $600. And what we've done is we are recording the lung sound from, this is just one of the students in the lab. So we're just recording her lung sounds, but we're simulating a noisy environment. So what you're seeing here is a sound meter that measures how loud the environment is. And so this is what you basically pick up with this top-of-the-line stethoscope when the environment is noisy. So you can basically hear the lung, but you mostly hear the environment. That's what the stethoscope is picking up. To contrast that, oh, thank you. Thanks, Najim. So to contrast that, this is our device. This is just a 3D printed version of it. Same environment, you can see from the sound meter how loud the environment is. Same subject, same environment, but this is the Hopkins device, and this is what you pick up with this device. So it's as if the environment has not existed, and that's basically something we're able to achieve, even though you can see how loud it is, the sound meter is giving you an indication. And then who prefer the other. It's tricky because, to be able to diagnose things like pneumonia with certain patterns, sometimes you don't want too much filtering. So I think part of the art of this is you want to filter the noise, but you don't want to filter the sounds that may sound like noise, but are actually telling you the person has pneumonia or something like that. So it's not a trivial just filtering procedure. There is, a lot of tricky tweaking that goes on into that. And then the last thing we're able to do now that we have this microprocessor on this device is we can say, well, how well can we tell a person, a healthy lung from an abnormal lung? And so again, because we happen to know a thing or two about how to process sound and map it onto these high dimensional spaces, we sort of, in some work a few years ago, we were able to mimic the brain mapping of the sound along temporal and spectral dimensions to basically allow discrimination between what a normal lung pattern should sound like and an abnormal one. And these are basically the kinds of results we have. So in red is the system, and here on the y-axis is the performance, sort of higher is better. This is how well the system, about 90% of the time, it can tell whether this is a normal or abnormal lung sound. And this, at least the results at that time, in 2015, this is basically how it compares to other systems that existed at the time. This is obviously an ongoing research topic, and by now we're able to perform much better than this, but there's a lot of validation and evaluations you have to do, And so to finish off, this is obviously an ongoing and body of work. There is a lot of work that goes on the sensor side, trying to improve even more our ability to pick up the sounds or to envision long-term implementations of this device, either as a wearable or as a textile. But there's also work on the AI and biomimetic diagnostics, to further refine how well we can tell different patterns of the lung abnormalities, or to further refine our ability to tell different diseases from each other just by judging the differences that these impose on the patterns of the lung sounds. So to finish off, as we look forward and think about where this work has been leading us, I hope I sort of convinced you, if you haven't thought about this topic, that everyday communication is really, though it seems effortless, it's a really challenging, complex feat. And so as we think about what we've been learning from the brain, technologies really need to they have a lot to learn from how the brain functions by adopting these more adaptive, self-guided behavior and learning, because that's what allows the brain to be so nimble and so, adaptive to these environments. And eventually, this is how we want technology to evolve. So to finish off, obviously, this is work that has been done by a really large group of very talented students and postdocs that I've been lucky to work with, as well as a lot of collaborators and a host, I guess, of funding sources that have supported this work throughout the years. And then with that, I thank you very much for listening.
Thank you very much, Mounya. I think we have time for some questions, and if you have questions, I'll try to get to you with the mic so that the folks who are online can also hear the questions as well as the answers. So, any questions?
Thank you. Thank you, Mounya, for such a lovely talk, and thank you for being a colleague all this time, and it's been wonderful having you in the department. My question is to do with one of the figures that you put up with the vest.
Mm-hmm.
It seems like the sensor was on the right-hand side. Was that intentional, or is it just reflection in the?
You mean just these?
Yeah, these guys.
Right.
Is it the right? I mean, yeah.
Yeah. So this is just a schematic. That's not the necessarily the idea. You basically will get better pickup from the back than you get from the front because of the effect from the heart if you're focusing on the lung. And one of the things, if you notice in our noise processing, is we also remove the sound from the heart because we're trying to ignore the heart, and the heart can overwhelm. So heart sound suppression, if you see it there, is something we're suppressed if you want to really focus on the lung. But so obviously the positioning plays a huge role in this. And one of the things we were hoping to do is to compare the information across the different sites, but also down the road to envision a wearable version. There is a lot of complementary information you would get from these different sites. So yeah, so that was just a schematic, not necessarily reflective of a, yeah. Sure, thank you.
So thank you. Really interesting talk. So my question has to do with sort of active sensing with acoustics. So here you are trying to detect something which you don't really have any cues on, right? In an active sensing situation, you actually kind of have some knowledge of the signal that you've sent. And we know that, for example, in the underwater environment, the marine mammals are able to detect things that we can't with our best sonar systems. So I'm just wondering if there's lessons here for us in the acoustic sensing.
Absolutely. So, I mean, I didn't get a chance to touch some of the, so we have an ongoing collaboration on a biosonar system where we're basically trying to learn from the bats as a, as a echolocating animal. And that actually bears a lot of interesting lessons for us as we think about, even though the bat is a mammal, it is a sort of a specialist type of a mammal. And so that imposes certain constraints in terms of how you infer the information from those signals. And so there's definitely a lot of interesting implications of that work applied specifically to sonar applications. Yes.
Any other questions?
Say something about those cloth.
Right. So this is sort of
exactly is this for?
So this is, I guess, some of the future work eventually. It's basically weaving into the cloth these kind of materials that would allow sensing. So one of the fascinating things about this work with the sensors, this is, by the way, a collaboration with Jim West's lab, is there is a lot of interesting ways you can pick up. So one of the challenges with stethoscopes is what they're doing is they're really picking up sound from air. So they're trying to come as close to the chest as possible, but the energy is really transferred from basically the skin into the air, and then the material you're trying to get as close as possible. So you're going through these two stages of transformation, which loses a lot of energy.
The thread acts like a microphone?
Yeah, so it's basically like a transducer, or you can think of it that way. Or actually one of the more sort of closer implementations that's happening is basically a new transducer that adapts its acoustic impedance to match the skin. And so this way you don't have to go through air. And by not going through air, you don't pick up anything from the surrounds at all. And that should, in theory, if all pieces fall in place, it should, in theory, you don't have to do any noise cancellation at all, because you're not picking sound from air at all. So that's, there is, I think, a lot of opportunity. And that's sort of one of the reasons, these devices, I think, are interesting, but can have a large impact, in these different domains where we're trying to apply them.
So if there are no more questions, first of all, let's thank
Thank
Mounya
you.
once again.
Instructed to come here.
We have a memento of this event.
Thank you.
Congratulations.
Thank you. Thank you.
Congratulations again.
Thank you very much.
Thank you all for joining us. This is a very auspicious day because with the slight relaxations of COVID rules, those of you who are here, sorry to all of those of you who are online, those of you who are here can get a celebratory cupcake to take with you. So, thank you all very much.
Thank you very much. Thank you very much.